Welcome back to Trigonometry. In this video, I would like to move to another chapter of the textbook, and in this chapter I want to talk about another math concept which belongs to different branch of mathematics. And this branch of mathematics is very hard. It's so hard that a lot of mathematicians spend their whole life doing research on that. This branch of mathematics is called vector analysis. So in this course we want to study a vector, okay? And as I say, vector is another branch of mathematics. Then why we include vector in trigonometry? As you know that the purpose of trigonometry is to measure the length, the side of the triangle, and to measure the degree of the angle. For example, or you can measure the side of the triangle or rectangle. You want to calculate those sides. Okay. For example, I want to measure the length of this whiteboard, right? And I use this and I measure. I say that this is 4 feet. Okay, this is 4 feet. This quantity, 4 feet is the number. This quantity, we call that scalar quantity. Okay, and there's another quantity when doing research on vector, we call the vector quantity. So I'm going to talk about next. I'm going to talk to the first part of this lecture. I want to talk about the difference between the vector quantity and scalar quantity. So go ahead and write down the name of the topic today, vector. Okay. So the first part, I'm going to do some intro. Okay. So scalar quantity involve a number. Okay, for example, length of this whiteboard is 4 feet, or I can say the volume of the cube, okay, is 18 centimeter cube, something like that. Okay, or I can say the area of the triangle is 20 meters square, for example. Those quantity, those number, we call the scalar quantity. Okay, so scalar quantity. Okay, scalar quantity. So scalar quantity involve a number. Okay. They're just number. For example, area of triangle. Okay, volume of a cube. Okay, this is, I'm gonna throw this away. It isn't working anymore. Okay, volume of a cube. Okay. So it doesn't have any. It doesn't include direction over here. But there's another quantity that involve number and direction. I don't know if you guys noticed that. It's in your every hour of your life. You know, you spend your life outside, right? You drive the car, right? And one of the quantity that including that involving number and direction, it is vector. It is velocity. I'm sorry. And those quantity we call vector quantity. Quantity. Okay, that involving magnitude, I can say, or number, and direction. Okay, go over and for example, velocity or velocity, acceleration, or force. You will see this quantity when when you learn in physics. Okay, because we have to consider direction every time we're talking about velocity, every time we're talking about the force or acceleration. We also have to consider direction, because the force could be the upward force or downward force, or every time we're talking about the gravity, right? Gravity of the earth, right, is always toward the center of the earth, of the center of the sphere of the earth, right? So that includes direction. Okay. So those are vector quantity. But in order to understand vector quantity, we need to know what vector is. We need to know what vector is. So on the second part, I want to talk about the vector itself. Okay, the vector definition. I want to talk about definition. What is vector? You need to understand that. I already say vector quantity has direction. And every time, remember, you guys talking about direction, right? You know that, okay, this upward, downward, left or right, right? And every time we think about upward, downward, left or right, we think about the coordinate system. Okay? Then what is vector? Okay. How we create vector? For example, I have a 2D surface, okay, 2-dimensional surface here. Okay, and on this 2-dimensional surface, okay, 2-dimensional surface, I pick 2 points. Okay, I call point A and point B. Okay, and I want to connect these 2 points together. Okay, I connect 2 points together. If I connect 2 points together, what did I create? I don't know, you guys remember the concept in geometry. If we have 2 points and we connect these 2 points, it gives you what? It gives you a segment, right? It gives you a segment. So on my surface here, I have segment AB. Okay, but at B, I draw the arrow. Okay, at B, I draw an arrow. So what I just have on my whiteboard here is a segment AB with a direction. Okay. If we draw a segment and you draw an arrow, you create a vector. So over here we have vector AB. Okay, vector AB. And vector AB is notated as, okay, notated as AB, okay, and with the arrow like that, vector AB. Okay. Okay. And because vector that involves number and direction, every time we have a segment, we might know the magnitude, the length of that segment. For example, I measure this segment here, AB here, and I say this is 6 inches. This is 6 inches. So the length from A to B, okay, not including the direction, okay, we call the magnitude of vector AB. Okay, so magnitude, okay, of vector AB is the length of segment AB. Okay, this is a symbol for segment. Okay, and it's notated as magnitude. Okay, it's like an absolute bar of vector AB. Okay, for example, in this case we have magnitude of vector AB over here is 6 inches. Okay, it's 6 inches. So you can draw a bunch of vector in my 2-dimensional space. Okay, I can draw like this. I call it vector A. Or I can draw like this. I say this is vector B, okay? And I can name anything I want, okay? It doesn't have to be like this, okay? Then what is vector? Well, vector is just what? It's just what? It's just a segment with direction, that's all. So vector is a segment with direction. It's a segment with direction. Finally, okay. And because this is a segment, because they are segment, and in space, we have congruent segment, right? We have, for example, I draw two segments, and each segment is 6 inches. So I have equal segment. Okay, that's the definition of congruent segment or equal segment we already learned in geometry. Then how about vector? Do we have the same concept, the same definition? Is a congruent vector or equal vector the same definition as equal segment or not? Let's consider that. And those, when we consider that is one of the property of vector. Okay. We also talked about the opposite vector or parallel vector. That they are all property of vector. Okay. So on the third part, I want to talk about property of vector. And the first thing is equal vector. In what condition two vectors are equal? That's what we need to investigate. We know that equal or congruent segment when they have the same length. But how about equal vector? Is it the same as equal segment or not? And they say that two vectors are equal if two vectors are equal if they have the same direction okay, and the same magnitude. Okay, so that's the difference between equal segment. When we talk about equal segment, we're just talking about the length of that segment, okay? But when we talk about equal vector, we also talk about direction. It must be the same direction in order for two vectors to be equal, okay? Not just the length, not just the magnitude. So we must satisfy two conditions. First of all, the same direction. Secondly, it must have the same magnitude. Okay? Then we say that two vectors are equal to each other. For example, I have a vector that looks like this. Okay. I call it vector A. Okay. And I have another vector that looks like this. I call it vector B. And I measure this vector and I say that the magnitude, the length of the segment are the same. Okay. And these two vectors pointed toward the same direction. You see, they pointed to the right direction. Okay. Then I conclude that vector A equal vector B. Okay. A equal. How about like this? If I have a vector A that looks like this, and I had a vector B I measure the length, the magnitude, and of the vector A, and I say this is 4.5, and I measure over here, and I draw another vector, and I do is 4.5 also. Oh, I'm sorry. Okay, 4.5. Okay, and I call this vector B. Okay, so the magnitude is the same because I just measured. I measured both of the vector over here 4.5 inches. Okay, however, the direction is not the same. You see that one of the vector that pointed upward like that, one is pointed like this. So the direction is not the same. If the direction is not the same, then we cannot say these two vectors equal to each other. So this is vector A is not equal to vector B. Okay, this makes sense? Alright. Okay. Okay, so if we have in the same direction, we say that, and the same magnitude, we say the vector are equal to each other. Then what if we have different direction? Okay, but not in this case. What if we have one vector is pointed to the right hand side, the other vector pointed to the left hand side? Then what do we call? Okay, what we call? Okay, we will call it opposite vector. Opposite vector. It means that one vector is pointed to the right hand side, the other vector pointed to the left hand side. So we have vector A that look like this. Okay, and we also have another vector that look like this. It can be longer, the magnitude could be bigger or smaller or the same, but the direction is pointed one to the left and the other one to the right. Okay, so I call this vector B. Okay. So I say that vector A is opposite of vector B. Okay. Oh, we have something like this. We can say it is opposite to each other. I say vector A that look like this, and vector B the same magnitude as vector A, but they pointed toward the left side. They pointed to the left side. Okay. So vector B that look like this. So I can also say this vector A here is opposite of vector B. Okay. So in this case, because they have the same magnitude, even though they point to different direction, I can write vector A equal to the minus of vector B. Okay, minus of vector B. They're still opposite to each other. Okay, but I cannot say they equal. Okay, even though the magnitude is the same, but the direction is different, so I cannot say they are equal. But they still opposite to each other. Or I can have another example that is, I have one vector going this way. Okay, and another vector is on the same line. It's collinear. Okay, and I call it vector AB, and this vector AC. Okay, so vector AB is opposite of vector AC. Okay, it's opposite of vector AC. So because you see that vector AB pointed to the right hand side and vector AC that pointed to the left hand side, the opposite. However, if we do like this, if we draw another one and AC on this side, for example, instead of draw AC to the left hand side, I draw AC to the right hand side, okay, then we're not gonna say that they're opposite to each other anymore, okay? Okay, we're not gonna say that anymore. Okay. In that case, we will call it parallel vector. Parallel vector. So on part C, I want to talk about parallel vector. Vector is one of the hardest concepts in mathematics. However, vector is the foundation of advanced mathematics. Okay, you see vector in many word applications in physics. You probably see it in chemistry too. Okay, so vector is very important. That's why I want you to stay focused on the lecture, and I want you to learn this carefully. Okay, so part C, I want to talk about parallel vector. In what condition two vectors are parallel to each other? We need to know. We need to investigate that. Okay. Oh, let me give you the example when they are opposite to each other. They're not opposite to each other. I'm sorry. So what if I have a vector like this? Okay, and another vector like this. Okay. So A and B is not opposite to each other. Okay. A is not opposite to B. Alright? It's not opposite to B. Alright. Parallel vector. How do we know that they are parallel? Two vectors are parallel to each other. As we learned in geometry, you learn two lines parallel to each other, right? If you have two lines parallel to each other, if they never cut each other, okay. But in vector analysis, when we're talking about parallel vector, okay, not just about that two vectors are parallelly the same way as we learn in geometry, okay? However, two vectors can be called parallel to each other if they are collinear. If they are collinear, they can be parallel to each other. For example, first of all, let me draw two lines. Okay, this is a line, and I say that these two lines parallel to each other. Okay, because it's never cut each other. Just imagine that. Okay. And on this two line, I draw two vectors. Okay, this is vector AB, okay? And over here, I draw vector CD, for example. Okay. So these two vectors here, I say that they're parallel to each other because they are lying on two parallel lines. Okay. So I can say vector AB parallel to vector CD. Okay. Okay, parallel to vector CD. Or if I draw only one line, okay, and on this line I draw two vector AB and AC. Okay. I also say that they are parallel to each other. Or I can draw another one, AD, for example. So I can say that AC parallel to AB is parallel to AD. They all parallel to each other because they collinear. They lie on the same line. So this is collinear. Okay. They lie on the same line. So either they lie on the same line or they lie on two separate parallel lines. We can call those two vectors being parallel to each other. Okay, remember that. And there are a real definition, okay, a method to show that two vectors are parallel to each other. Okay? If a vector A, okay, is parallel to vector B, okay, then okay, okay, let me not use the statement if. A vector A is parallel to vector B. This is equivalent to, okay, this is equivalent to, the first statement equivalent to vector A equal to scalar of vector B. Okay, scalar. So this is a k number. It's just a number. Okay. What do I mean over here? What I mean over here that you can show two vectors parallel to each other. Of course, not by just looking at the picture, you know, because sometimes again, vector is like geometry. It's like trigonometry. Sometimes if they didn't draw it in scale, it's very hard for you to know they are parallel. You have to show it algebraically. So you can show a vector A parallel to vector B if you can show A equal to a number times vector B. Okay? For example, you can show that vector A is twice vector B. Okay. If you can show vector A is twice vector B, you conclude right away that vector A parallel to vector B. Okay. So if you can show that A equal to a scalar is a number, we already talked about that, a vector B, then we can conclude vector A parallel to vector B. Okay. Okay. For example, let me do the typical example. Example 2. This is example 1. Okay. I have an arbitrary triangle like this. ABC. Okay. And I picked a midpoint of AB. I call it point M. It's a midpoint, so it's equal to this. Okay, M is the midpoint of AB. Okay. So I want to show that vector AM, okay, AM is parallel to vector AB. Well, it's pretty obvious, you know, because you know that M is a midpoint. Answer. Okay. M is midpoint. Of AB. Okay. So AM vector equal to half of AB vector. Okay. And you see that AM, a vector equal to a scalar of another vector. So I satisfy this condition. So your k over here is a half. Your k. Okay. So you see that over here I can conclude that AM is parallel to AB because AM is scalar. It's a number of AB. The number could be positive or negative, okay? But you see in this case, because AM and AB has the same direction, okay? AM and AB, see that? Have the same direction. This pointed downward in the same direction. So over here we have positive number. If in the opposite direction, then we have negative number, okay? Alright, for example, I can write AM is negative half of vector BA. Okay? Okay, a vector BA, negative half vector. So I can say that vector AM is also parallel to vector BA. Okay? Because this is negative, it's a scalar number of another vector. Okay? And because we already know that every time we talk about vector, we also talk about magnitude. And magnitude is actually a number. Okay? Magnitude is the scalar quantity. And if we have number, we can add a number together, right? Or we can subtract a number together. Okay? So, the fourth property I want to talk about is addition of two vectors. Okay, how we gonna add two vectors together? Is it the same as we add number together or not? Okay, we want to investigate that also. Okay, so the adding two vectors. Okay. And there are two methods to add two vectors. Okay, the first method. Okay. Method 1, I call it method 1. So I have the vector like this. I have vector AB. Okay. Okay. Oh, I think I forgot to mention it. Vector AB, so the arrow position, we call it the terminal point, okay? And this point, the position A over here, we call the initial point. Sometimes we call that the tail of the vector, and this is called the head of the vector, okay? I should have put it in the first Roman, this, I think the second Roman of the lecture, but I think I forgot. Okay, so remember, B is called terminal point, A is called initial point, and A is the tail of the vector, and B is called the head of the vector. I'm sorry, guys. Sorry, guys. Okay, so A is the tail, and B is the head of the vector. Okay. All right. So I want to draw another vector. And I use the terminal point of vector AB as the initial point of another vector. Okay. So this is vector BC. Okay. So you see that the terminal point of vector AB is become the initial point of vector BC. Okay. So I have vector AB and vector BC. Now I want to add these two vectors together, AB to BC. Okay. Now I want to add vector AB to vector BC. Let me give you what? What? Okay, we'll give you what? What does it give you when you add vector AB to vector BC? Okay. So you see it over here that vector AB, we have B as the terminal point, and vector BC, we have B as the initial point. So we share B in common. When you add two vectors, okay, and you share initial point and terminal point, okay, then it gives you another vector, it gives you vector AC. Okay, so this is give you vector AC. Okay. It doesn't give you vector CA, okay? Remember, it gives you vector AC. So AC is A is the initial point, and C is the terminal point. Okay, so basically you just erase the part B over here, and you write A and C, the initial letter and the last letter. It will give you vector AC. Okay. So this picture is very important, okay, because the direction of this vector. Okay. If I change the direction of each vector, then you probably cannot add it anymore. Okay. Vector AB plus vector BC give you vector AC. That's what I want you to memorize. Okay. Then from here, if I give you a vector, for example, I give you vector E and F. Okay, I give you vector E and F. I can insert a letter in between so that I can split vector EF into two vectors. For example, I insert a letter K, for example. So this becomes vector EK. See, I insert a letter K in between. Okay, plus vector KF. Okay. So to give you the vector, then you can insert a letter in between so that you can split into smaller vector. Okay. So that is the first method to add two vectors together. Okay. A second method to add two vectors together, which we use the parallelogram rules. Okay, so I will erase this. Actually, the parallelogram rule is deduced from the first method. It's nothing other than just the first method. You know, but I mean, sometimes if we apply a parallelogram rule, it's easier because some students it's very hard to see, recognize the first method. It's very hard for you to recognize the picture of the first method. So method 2 is a parallelogram. Why we call it a parallelogram? Because actually we have to draw the parallelogram when you add two vectors together. Okay, for example, I have a vector AB that looks like this. Okay, and I have another vector AC that looks like this. So AB and AC, they share the same initial point. They share the same initial point. So it's different from this case. Okay, AB and AC share the same initial point. Okay, so based on vector AB, I can draw a parallel line. Okay, that parallel to AB. Okay, and I can also draw another line that parallel to AC. And these two lines intersect each other at another point. I call it point D. Okay. Then AD is considered as the sum of these two vectors. So AD is resulting vector. The same as this one. AC is resulting vector. When you add vector AB to BC. So AD is the resulting vector when you add vector AB to vector AC. So I can write like this: AB plus AC equal to AD. Okay. You use a lot of parallelogram rules when you do in physics, but in mathematics, most of the time you have to use the first method. Okay. Yeah, parallelogram rules is more like it's very helpful when you deal with application of vectors. So when you solve a lot of when you solve physics problem, you have to use a parallelogram method. Okay. So AD in this case is the resultant vector, and AC in this case is also the resultant vector right here. Okay. So why we need to learn these two methods of adding vector? Because it helps you to do the example. It helps you to do to prove math. I can give you the example here of using these two methods. I mean, most of the time it's the method 1. Okay. To prove the vector expression. On the test or on the final exam, I'm not going to give you the problem like this, but I want you to look into that carefully, because you will see the usefulness of method number 1, and you will see how I insert a letter in between so that I can split up into a smaller vector. Okay. Example. Given 4 points. Okay, this example is very helpful. Okay, it helps you understand vector better. Okay, A, B, C, D. I want to prove AB vector plus CD vector equal to AD vector plus CB vector. So what I have over here we call the vector expression. Okay. Proof. How we do this? Okay, so I'm going to use the first method. Okay, I'm going to use the first method to split up the letter. Okay, by insert a letter to split up a vector by insert a letter in between so that I can split up into two vector. So this is the vector expression, and there are three-way method to prove it. The same thing as you prove a trigonometry expression, right? You can do from left to right, right to left, or you can do from both sides. Okay, so I'm going to do from left to right over here. So I start with the left side. Okay. I want to show this equal to that. It means that I need to do some way so that I have AD plus CB. Okay. And I already told you that we are given a vector with two letters like this, initial point and terminal point. I can insert a letter in between so that it's split up into two vectors. So we want AD, right? We want AD. So I can insert a vector, I can insert a letter D here so that I have AD. So I can write AB as AD. So I use the method 1, right? Plus DB. You see that? I insert a letter in between so that I can split up AB into two smaller vector AD and DB. Okay? According to method 1 of adding two vectors. Same thing over here, we want CB. So I insert the letter B in between so it becomes CB plus BD. So what we have now, we have AD, okay, so we have a part of what we need to prove. We also have CB already, we have another part, okay. So I have AD plus CB, right? But we also have DB and BD. DB plus BD. Okay. How I'm going to deal with BD and DB. BD and DB. Just think about it. I have DB. You draw DB that look like this, right? And BD is actually the other direction, right? So we have the same thing. The magnitude is the same, but the direction is opposite to each other. The magnitude is the same and direction is opposite to each other. So basically it cancels them out. It cancels them out. So remember one of the example I gave you before. Okay. I think in the second part. No, it's in the opposite vector property. Okay, they have the same magnitude, they opposite to each other. So basically, it cancel out. Okay, so this is give you 0. Okay, because it's cancel out, give you 0 vector. So what you have left is AD plus CB, and we're done. So AB and BA cancel out, CD and DC cancel out because they opposite and the same magnitude, they cancel out. Okay, so DB, BD, they opposite to each other in terms of direction, and they have the same magnitude and they cancel out. That's why this gives you 0, and that's why we finished our proof. Okay. So this is an example, typical example of how we're going to use a method of adding two vectors together to do the proof. Okay, but other than just proving, method of adding two vectors is very helpful also in physics. Okay. Okay, so that is for adding two vectors. How about subtracting two vectors? Is it the same as adding two vectors? Okay, so part D, E, I want to talk about subtracting two vectors. Remember that when you add two numbers, for example, 2 plus 3 is the same as you when you subtract two numbers, I'm sorry, not adding. For example, like 5 minus 2. 5 minus 2 is the same as you add number 5 to a negative number 2, right? So 5 minus 2 is the same as 5 plus minus, right? Plus minus. Okay, you add number 5 to a negative number. Okay. So this is the same as this vector. The same as you subtract two vector. When you subtract two vector, okay, it's the same you add to a negative of another vector. Okay. Alright. Let's subtract these two vectors. I want to have vector AB, okay, minus vector AC, okay, AB minus AC. Remember, we share the same initial point, okay. Okay. Then this is give you vector CB. Give you vector CB. Okay. So if you look at in another way, you will see that if it given a vector, okay, I can split it up into two vectors using the subtraction method. Okay, I can insert a letter in the sense that the tail. The head minus the tail. Okay, the head of vector CB is B, the tail of vector CB is C. So if I insert any number, any letter, for example A, so it will become vector AB minus vector AC. For example, if I give you EF, okay, I can split vector EF into two vectors using the subtraction method. So this F is the head, E is the tail. For example, I use letter K, for example, then I can write head minus tail, so it becomes KF. See, KF is the head, right? Head minus tail, KE. Okay, KF minus KE. Okay. And subtracting two vector is also important. Okay, that's very important. Okay, we can use the formula and the picture to prove a vector expression. For example, okay. What if I want you to prove if AB vector equal to CD vector, then AC vector equal to BD vector. So I'm going to use the subtraction of two vector, okay, to prove this expression. Okay, so how we do that? So we know that AB equal to CD. So this is the first statement. I want to show the second statement. Then I have this. I know that CD can be written as, if I use the subtracting method, I can split it up into two smaller vectors using a ladder. Okay, so I can write CD as AD minus AC, or I can write CDs as because we want BD, right? So I can use letter B to insert. So head minus tail, so this is the head, and I use letter B. So you can use anything because this is what we want. Okay, we want BD. Okay, we want BD equal to AC, so I can use letter B. So I can write it BD minus BC. Okay, head minus tail. Head minus tail. Okay. And AB, same thing. Okay, because we want AC, right? So I can write CB head minus CA. Okay, that's all right. I mean, we want AC, but if we have CA, we just put a minus in the front and just switch direction. Okay, and we already know that AB equal to CD. We know AB equal to CD. And therefore, this implies CD is this, AB is this, so we know that CD minus CA, right, equal to BD minus BC. Okay, because AB is this, AB is this, I replace that. CD is this, I replace that. Okay. All right. So what we have here? So we have BD. Okay, this is what we need, right? We already have a part that we need. Okay. We want AC, but over here is CA. That's all right. So CB, I can change the sign, then I can flip the direction. Remember, because AC is equal to, AC vector is equal to the minus of CA vector. Okay, they cancel out. Alright, so this becomes AC, and then BD We already have it, minus BC. Okay. So what we have AC equal to BD already, right? And you see here, CB, I can rewrite it as CB, I rewrite everything. Okay, BC, I can change the direction by put the minus sign in the front. So minus minus becomes CB. See, I change the direction, right? I change head to tail, become tail to head, and I can switch the sign. So now CB and CB cancel out. Okay, so I have AC equal to BD. And this is what we have. We're done. Okay. So we're successfully using the subtracting method to prove this statement. For the proven part, I noticed it took you kind of time to get used to it because it requires a lot of practice. However, I want to give you this example so that you understand that the subtracting two method and adding two vector and subtracting two vector is very helpful. It's to help you to understand vector better. Okay, but on the test, on the exam, I'm not going to give you the proving problem. Okay, it's for you to understand better subtracting method and the two method of adding two vectors together. Okay. All right. So after we learn adding, subtracting, we can generalize the rules. When you add in two vector or subtracting two vector together, the same thing as we have the general property when you add in two number. Okay, so on the next part, we talk about basic property. Okay, basic property. Let's say we have the same property as we do when we add in two real number together now. Okay. So if we have vector A, we added to vector B. It is the same as vector B added to vector A. So this is called a commutative property. Okay. Commutative property. Commutative property. Okay. If you have vector A plus vector 0, it's the same as vector 0 plus vector A equal to vector A. Okay. We also have associative property. We have vector A plus vector B, the sum of vector B and vector C, that is equal to the sum of vector A and vector B plus 2 vector C. Okay. So this is called associative property. Okay. So it's kind of the same thing as the same property as we add two real number, two integer together. Okay. We also have commutative, associative. We also have transitive also. If we have vector A equal to vector B, okay, and vector B equal to vector C, then vector A equal to vector C. This is a transitivity property. Okay, transitivity property. Okay. Alright. Okay. Okay, so we know that when we add two vectors or we subtracting two vectors together, it gives you another vector. Then how about if we multiply a vector by a number? The question is, if you multiply a number by the vector, it gives you another vector or not? Okay, let's see about that. Alright, so next part G, I want to talk about multiplication between a number and a vector. Okay? Alright. Okay, let me give you a vector A. Okay? And a vector A that looks like this. Okay? This is vector A. And I want to multiply this vector by 2, so I have vector 2A. So if you multiply a vector by a number, by the scalar, that number could be positive or negative. In this example, I'll give you a positive one. Then it also gives you a vector. Okay? But how is that vector compared to this one? Okay? This vector will have the same direction as the original one. So they have the same direction, and the magnitude will be twice the magnitude of the original one. Okay? So this will be vector 2A. So if you multiply a number by the vector, it gives you another vector. Okay? The magnitude of that vector is bigger than the original vector. Okay? Sometimes it's smaller if you multiply by half. So for example, if I have multiplied A by half, okay, it gives you another vector the same direction as the original vector, but it's just half, the magnitude is just half. Okay, just half of vector A. It's just half of vector A. And let me redraw it here. Here you go. The magnitude is just half. I mean the length of the segment is just half of vector, the length of the vector A here. Then if you multiply by a negative number, the magnitude will be different. Yes, it could be double or half. However, the direction will be opposite direction. Okay. For example, if I multiply by negative 3A, by negative 3, then the new vector will be 3 times bigger than the original vectors. Okay, and the direction will be in this direction, this opposite direction. Okay, so you remember that if you add in two vectors or you subtract two vectors, give you another vector. If you multiply a number by a vector, it also gives you another vector. Okay, and from that understanding, we can generalize all basic property of multiplying a vector by a number. The first property, okay, is if you multiply a number k by a vector LA vector, then it gives you KL A vector. If you multiply the sum by the vector, then you can apply distributive property, then it gives you MA vector plus NA vector. Okay. If you multiply a number by the sum of two vectors, over here vector A plus vector B, then it gives you vector MA plus vector MB. Okay. And of course, if you multiply the 0 vector by the vector A, a 0 by the vector A, then it gives you 0 vector. 0 times vector A is the same as vector A times 0. And of course, the same as 0 vector. Or if you multiply by 1, 1 times vector A is the same as vector A times 1, and it's the same as vector A. Okay. Okay. Alright. So this is a basic property for multiplying the number by the vector. And so I think that's all for the first lecture about vector. I know it requires you to do a lot of practice to understand vector, and I hope that all the problem is in the homework it is enough for you to understand it. As I told you, all the proof problem I'm not going to give you as the problem on the test or example or the exam, but I want you to look into that so that you really understand the adding and subtracting between two vectors. Okay, so that's all for the lecture today. If you guys have any question, again, post it on the discussion board. If you can find that you have any careless mistake, let me know. Okay, and last time a couple of students found out that I have careless mistake, and I already fixed that. I was very happy that you found out some mistake. It happens, you know. Yes, let me know right away. Post a question on the discussion board so that everybody can discuss and everybody can contribute and everybody can get the answer for the concern, okay, you have. Okay, that's all, and I'll see you next time. Okay, bye bye.